Okay, so my name's Jared Smith. I'm really glad you guys are all here today. This is the first time I've given this particular talk, and I'm also a little under the weather, so just bear with me if I stumble or whatever. The flu is going on very badly back in Knoxville, but I don't have it yet. I just have a cough, so hopefully it doesn't get much worse. But I'll be talking about big data analysis, and such a buzzword, but just basically data analysis in Python. It's actually really easy and a lot of fun. But mostly we'll be focusing on Apache Spark, which is a distributed analysis framework that just happens to have a great API. Python is designed specifically for Python, Scala, and Java, as well as R and some other stuff. And I work at Oak Ridge National Lab. So first I'll tell you a bit about me. I'm a cybersecurity researcher and project lead at Oak Ridge National Lab. We're the DOE's largest national lab, originated when the atomic bomb was built. We do nuclear science, energy science, and environmental science. We do supercomputing, lots of stuff. It's a cool place. If you're ever interested, it's in Knoxville. Come check it out. I'm a PhD student at UT in Knoxville as well. I work in computer security. I founded our security club. It's now about 90 members. Active members in the hackathon we had, and some of you here might have been sponsors. Eventbrite was a big sponsor. We had a lot of other people as well. I'm a technical mentor at the Knoxville Entrepreneur Center, and that's just go and help out with our hackathons and bring in business people from all over East Tennessee, come together and build really cool stuff. And then finally, there's a little list of my interests of security in the order of green of what I'm most experienced with to less. We do have a vehicle security lab at Oak Ridge. We drive up a vehicle and get into it remotely and all kinds of fun stuff. Python is a favorite of mine, and I can write it. Machine learning, just pretty much an enthusiast. I'm not an expert. Malware analysis, and I do like to write other languages, most notably C and C++ and Java. Just messing around a bit with Rust and Go. They're great languages if you have time to check them out. So, what is big data and why is it so important? There's a quote that I pulled up from the guy that founded Lotus Software, which if you remember, I was just born when that probably went out of use, but I heard it was a big tool back then. And he said getting information off the internet is like taking a drink from a fire hydrant, and that's very much the case. In fact, Twitter calls its API the fire hose, like all the tweets that come out, which is millions and millions a day, if not more than that. They call it the fire hose, and you have to pay a lot of money to get access to it. We live in an internet where information is key and is business value for companies. And if we know how to deal with that information, we can add a lot of value. Just like we heard Sarah Guido's talk this morning, data science is a really booming field. And I hope to give you a little bit of intuition to how you do it in Python. So again, that's Mitch Gafur that Lotus Software did. So why data science? So we have this way to analyze data. That's basically what it is. You analyze data, and you try and pull trends out of it and pull insights out of it, and you just try and make sense of it and provide value for whoever your customer is, or yourself if you're just looking at doing analysis with it. It enables us to do things like those, and again, Python is a great tool for this, but unfortunately when you have lots and lots of data, Python isn't the best solution. But there are things that latch onto Python, like Spark, what I'll talk about, that do add a lot of value. So there's the 4 V's of big data. And the first one is volume. And volume basically means that we have lots and lots of this data. There's a ton. Petabytes a day are processed at most of the major companies. Netflix has hundreds of petabytes of data in their cloud. There's a lot. So that's good to remember and why it's actually important. Velocity is another one. So data comes in extremely quickly. If you think about the rate at which Facebook sends posts down their pipes, it's incredible. They have to have their own data center just because of that. And they're at the point now where they're building their own networking hardware. They won't even use Cisco, which is used for basically everywhere else, because they want to customize it perfectly to their own need. The variety of data is wide and very distributed. So we have structured data like Excel files we're getting more into like documents. And then we've got very unstructured data like tweets, which could be all kinds of words that we have no idea what they mean. A computer has no idea what they mean. And it can contain Unicode characters, images, links. We have no idea what could actually be in there. In the veracity of data, this is relating to how certain we are about the data's actual validity and how truthful it is. So do we trust the data we're getting? Do we trust all of the events we're getting from our intrusion detection system that says we have an affected computer at this point in the network? Do we go disable their computer from getting to the network and spreading a virus? We don't really know whether the data we're getting is valid or not. So how do we actually handle that much data, and how can we specifically do it in Python? So the setup, I'm going to go through one code example, once with Python, once with Spark, and kind of show you the benefits of using Spark in this case. So our goal is, this is a somewhat realistic goal, but I generated the data myself. So we're going to compute the total price of randomly generated house data per zip code for all the US zip codes. So I downloaded every zip code in the US, and then I used Python to generate a long list. In this case, we're doing 100 different prices for each one of the zip codes. And there's something, I have it right here. So again, the file format, zip code, and then house price, that's a CSV file. And we have about 45,000 or 43,000 total zip codes times 100 house prices per zip code. That's about 4.35 million entries. And that's doable in Python, but as I'll show you, it's not really the quickest. So let's look at the code to actually take this and compute for each zip code the total price of all of those houses we have for that zip code. So you can think of this is an average. This is just if you have, your city, what's the total aggregate value or, worth of that city in terms of house prices. So we've got some pretty straightforward Python code here. First, we'll start by importing this great library called TimeIt. If you haven't heard of it, it's really good for just timing Python code. And then we're going to import CSV. And down here, we enter into the name. So in Python, you can say if the name of this file or this thing we're executing is main, then it will run that if you run it as a script. And so we're just going to get the elapsed time from this module by running Python. And that function Python is just that function. And apparently, you can name things in Python after the language and it won't freak out. But I don't know. If it did, I'd be pretty concerned. So basically, we're going to make a dictionary, which is that counts dictionary, and we're going to map a zip code. The zip code will be the key, and the value will be the total price for that zip code. And then from there, we're going to read in the CSV file using context managers, which that's what that with statement is. So withs basically wrap up a I/O operation or some kind of unsafe operation that will clean it up afterwards. So in this case, rather than opening a file and forgetting to close it, with will close it for us when we break out of that block, which would be basically getting out of that function. And so basically, we're going to read it in using the CSV library. And for every row in the reader, if we haven't encountered that row before, then we'll add it to the dictionary for that zip code. So that says if we find 37801 and we haven't seen a price for that yet, then we'll initialize that key in the dictionary as that price, so 100,000. And so it loops around again and say next time we get a different value, we get 37803, then we'll make another key in that dictionary with that value. And now let's go along a little more and we see 37801 again. So now we have 100,000 for that because that was the first time we saw it. And now we're just going to add the house price to the value of that. So counts row of zip code is going to give us the entry for that zip code, the price we have so far. So it'll add the next price to it. So basically, we're just reading a CSV file and counting up based on the two parts of the CSV file, the total price per zip code of an area, or for houses. So what does this actually take? How long does it take to do this? In pure Python, we're not using Python, we're not optimizing, nothing like that. It actually takes 15.71 seconds, which is not too bad for a, let's see, 4.35 million line file. But the stats for it, we're running on a MacBook Pro, so it's my computer right here. It's a quad core, but we're only using one core. This isn't in parallel, so that's a big thing that's biting us. It's just a 2.5 gigahertz processor, and if you really care, it's got 16 gigs of RAM. So that really sucks. We can't really do that well with that. Because imagine if it takes that many seconds to process a 4.35 million line file, how long will it take to process a 4 trillion line file, which I have dealt with before with Spark at Oak Ridge. It can get very crazy to do with just Python. So again, we can do better. So that's where Spark, it's a beautiful logo, plus Python equals happy. So what exactly is Spark? Spark is essentially a distributed processing engine that looks a little bit like this, and it's a lot to explain, so I'll start by just showing you the architecture. It is a Scala application that will take code and distribute it across a cluster of machines, or just your one machine, and execute tasks on those pieces of the cluster in parallel. So if I give a task to 5 of you, or I give 5 tasks to 5 of you, that's better than me giving 5 tasks to 1 person, because if you can all do them at the same time, or in the same amount of time, it'll be that much quicker than letting 1 person stop and then do the next one and then keep going. They'll all be done at one time. So essentially, Spark is built of a core, and then we have to schedule these tasks on top of Spark. So I'm going to show you in a second that code we just wrote. We can throw that on Spark, and it will schedule tasks to do each of the individual accumulations inside that data. And so you can run on a standalone scheduler, which can run on just your machine. You don't have to install anything. Yarn, which is this great thing that Hadoop, which is Hadoop going back a bit. When Google first implemented their search engine algorithm PageRank to show you the ranks of pages on the internet, they used something called MapReduce. And they published a paper about it, and some awesome people wrote Hadoop based on that. And Hadoop is kind of like Spark, but it's kind of an older version. It's still very much used, but Spark is kind of a build on that, taking all the best things from it and building on it. But it still runs on it underneath. And Yarn, after all of that, is just a scheduler that Hadoop uses. And Mesos is another Apache project. So when you see these Apache projects like Spark and Flink and Mahal and Apache, the actual server, all of these things, they're open source projects under the Apache Foundation. Very similar to that of Continuum Analytics and the NumFocus project, who do Pandas and Matplotlib and scikit-learn and all that stuff. So basically, in terms of speed, it uses a directed acyclic graph, which is a long term for something from graph theory, where all you have to really get out of this is that it's all behind the scenes, and it will build a list of tasks optimally and execute them in a way that is transparent to you very quickly. In terms of usability, there are over 80 high-level operators for building parallel applications. We'll go into this in just a second. So things like counting up on your data set, or taking the mean of it, or combining different things by the key of your data, or basically mapping or reducing. If you guys are familiar in Python, there's map and reduce. They can do that across much more data. So the building blocks of this application, or of Spark. So we have tasks, like I mentioned before, which is basically just a piece of computation. It could be just a function that literally adds a character to a string. So like another example is a portion of a data set that needs to be filtered, and filtered is just the functional Python thing for basically pulling some data out of a list. That can be done in a task. Another building block is a stage. And a stage is essentially a set of tasks that define execution inside that directed acyclic graph. So when Spark will automatically, without you knowing, build stages of operations that can be run on different nodes in your cluster and organize them in a really pretty graph that's directed, meaning it's pointed, it's not just, it has arrows on it, and it's acyclic. And when we say acyclic, we mean it doesn't have cycles. Okay, so and another example is by doing a filter of a data set in one stage, it could say, hey, I'm going to throw this filter, I'm going to filter out some stuff from the list in one stage. And the next stage is going to be shuffling, which is basically Spark's way of moving data around to put data between the two previous stages into one. So it separates these because it can do them across the cluster in parallel without you knowing, and do it much faster than you writing Python code yourself and SSHing into a server and running it there and coming back and breaking because of a race condition and all that other stuff. So essentially, this is another picture that defines that. So Spark has a cluster manager. I told you you could run it on your computer. You could run it on Mesos or Yarn. It really, you download Spark and you do /run, and it's already, you don't even have to worry about thinking about this. But just to get a sense for what it does. We have a driver program, which if you think of your Python shell, there's a shell called PySpark, where you can run this in just a shell like you would with Python already. And it essentially talks to a bunch of nodes, and those nodes have workers on them, and something called executors, which basically executors are a wrapper, an abstraction around tasks. So all of this is just a big mess of garbage to basically say we can make your Python code a lot faster for lots of data. And again, a Spark driver, which is your machine, if you have a cluster of 8 machines and you're SSH in the machine 0, the driver will run there, and it will use those other 7 machines as workers. So the semantics of Spark, this is the last really stupid technical stuff we have to get out of the way. The principal data structure is an RDD, which in Spark language, that means a resilient distributed data set. The people that designed this were PhD students and professors at UC Berkeley, way smarter than me and anyone I know at my university. So they picked some really tough words. That's all I'm trying to say. RDDs have a lot of operations on them. They have mapping and reducing and counting and max. And then anything you can think of doing on a list of items or a dictionary of items, it can do for you. And you can define your own if you want as well. And more advanced operations, things that I won't even touch or go into. Like, you can apparently do a left outer join between two data sets as if we have like SQL tables. There's lots of crazy stuff. And you can see why all these primitives would be useful for data scientists. If they have a bunch of data, well, there's a talk, I met her earlier that she's giving on Oscar nominations and picking out winners and who they came from. So if you have a long list of movies, and there's information about each movie, if you have a key, which is the name of the movie, and the value is a list of actors in that movie, and you want to tell which movies have the highest quality actors in them, then you might use something like combine by key to go through all those things and combine actors with certain attributes into one key, stuff like that. And I'll go in here and show you that in a second. Okay, so with me, this can be very confusing. It took me like 3 months at the lab to learn all of this and get it working on like 4 trillion data points for a data set we had. So we're like really going fast, but I promise you don't have to know all of this to actually work with it. So the assumptions about our little test simulator scenario of rewriting the other code in Spark. So we're going to assume that you downloaded Spark from their website, and it's just a zip file. You unzip it, and you have the binaries there. You're running Spark in standalone mode, which means you can run it on your computer and not have to pay for like 8 machines. But if you do want to pay for 8 machines, you just go to Amazon, and they have a service that is just Spark in the cloud. Or Google has one, IBM has one, everybody does. You're using PySpark, which I hope you are. It's just the Python API. If you want, you can use Scala, or if you really don't like yourself, you can use Java. Or if you really, really don't like yourself, you can use R. I don't know who would do that. Statisticians would disagree with me there. It's an okay language. The Spark submit executable, which is basically saying, hey, Spark, take my Python file and process it. That's accessible through your terminal, which we need to run PySpark jobs with. So we're going to go through the code here, which looks like a lot, but we're going to take this one step at a time. It's a little longer, but we're going to go through it. So the first step, again, we're importing our timeIt function in our CSV library. And then we have this great library now they're running on Spark called PySpark. You don't have to pip install it at all, because when you submit this file to Spark Submit or run it with the PySpark shell, it's already going to load in the PySpark binary or the PySpark Python package. And we get some config stuff out of it. And then we set up our Spark config. Spark has a notion of a context. And a context is basically just a wrapper for all your variables, how you define the job, the number of executors, the name of the app. You can see here we set the variable spark.executor.memory. That is actually a Java virtual machine argument that will get passed in, and it will set the memory of our executors that run tasks. It will give them 1 gig max of memory, which when you do lots of data, these are things you want to tweak, because if you crash in a node, you'll know why. It might run out of memory, might run out of threads, something like that. We're doing this, we're reading in the data now before we actually time anything, because Spark doesn't need, when we think about Spark, the assumption is that you've already got all your data, and the actual computation is what you're actually going to be timing, because you're going to have all your data loaded on your machine in a file system, and Spark, and I'll show you in a second, can just read that off of disk. But before, we had to iterate over the dictionary and go through it one at a time. The option before would have been instead just to load it all into a list, but I wouldn't have really made much of a difference, because we're just going over it one at a time. So again, we're going to read each row in at a time, and we're going to make, this time instead of a dictionary, we're going to make tuples. So we have a tuple of a zip code and a house price. That's basically what we have there. And then finally, this last line, SC is a Spark context, and parallelize means, hey, take my data set that lives in memory on Spark, or on my machine, which is just a Python list, and turn it into an RDD, a resilient distributed data set, the Spark primitive. It will take that, and when you call that method, it will distribute that data across all your nodes. In the case of a standalone scheduler, like just my machine, it's just going to be 1. Or if you want it to run concurrently, it can be multiple too. Well, in this case, it will run concurrently after the number of threads or processes I have, which is 4. And we have to do this really cheeky stuff to wrap the arguments because the time it module is really dumb. I realize I kind of thought it'd be cool to show you guys, and it's useful sometimes. But to actually pass in variables to our function Spark right there, it takes this context and the data, that RDD. So to get that into there, we have to actually just define a wrapper function, which don't worry about this. This is advanced Python. If you're not familiar, you can look it up. Essentially, we're just passing a function that has our data in it. You can do this other ways. You don't have to do this if you're not timing it. And then here's the function of all functions. And just calling it Spark. And to do that same operation we had before, where we got the sum, for each zip code. Now all we have to do is on our RDD, we call combine by key, and we pass it 3 functions. And I'll explain those right now. So in this combine by key function, essentially what it does is for every single tuple in our data set, which is just tuples of zip codes and house prices, it's going to put the unique zip codes into their own entry in a dict, or in another tuple, and in the value in the second part of that tuple, it's going to sum up all of those house prices for that. And the function definition is down here, and it's really tiny on purpose. You're not supposed to read it. But all I had to do was Google, hey, Python Spark, sum up keys in dictionary, and that code, someone had already written in Stack Overflow is right there. And I'll explain it, each of the arguments right now. But again, to ask you to understand this is like asking you to go and really read a lot about Spark. But again, all the things I've told you, with a little bit of practice, you can figure it out. The point is how much quicker it is. I'll show you in a second. So the first argument is just we take the value and we initialize it. It's called create combiner. So we take the very first thing in that list we see and just give it the house price. So we started off at the house price that we see. The merge value function will take any two existing things and combine them, just how you would think. You have zip code that's 37801 with house price 100,000. That's a tuple. And then you have a zip code that's 37801, the same, and house price 50,000. It will take those and smash them together into 150,000 for 37801. And that second function does it on a partition. So a partition might have a bunch of these zip codes. And the third function, all it does is sum up across all partitions. So Spark, this is the glory of Spark, is that we actually run in parallel across all our machines without having to think about it at all. And the documentation will tell you how to do that. It's a lot to take in. So how quick is that actually? It's actually 3.5 seconds. For that same, what was before 15 seconds, it's now 3.5, and that will scale linearly going up. It's not going to go exponentially or jump or pop out in your face and mess with you. It will work. And trust me, I've actually done this. I'm not lying. And the machine stats are the exact same, but now we're running with all of our cores. We're distributing it across our system. And just imagine if we ran that same job in a machine of 8 nodes. The cluster we have at the lab, just for my group, not the supercomputer, they've got way bigger stuff, has 64 gigs of RAM on each node and 32 CPUs in each node as well. So if you have a sufficiently large data set, the overhead of shoving that data across all of those will be completely blown away by how fast we run. So we're very happy. I love this new emoji. It's like literally the best one possible. I can't think of a better one. Does anyone agree? Does anyone like it? Does Android have it? Yeah. Yes. Do they? So when Apple makes these new emojis, does everyone else just have to deal with it? Or is there's a standard, right? Okay, do they all just like get... Android just has a different icon, that's it. Yeah, but do all the people... Do the developers that write emojis, their job is like just to keep up with this standard? Is that it? Like, I know, that'd be a bad job. I'm sorry if any of you do that. So what about real data? Again, I mentioned that this was like 4.35 million lines. That's like chump change compared to what we could actually do with this. So the power of Spark is great. Again, I said it runs on top of existing Hadoop clusters. The cluster we're using uses Yarn. It's a schedule I talked about before. And that Hadoop is based on Google's MapReduce paper. It's a pretty readable paper, along with most of the stuff by Google, unlike going to some academic professor and they throw proofs everywhere and you just hate yourself for being a computer scientist because you don't know math. Like half of computer science degrees is just pretending to know math because you don't know it. I can tell you that. You can get through a PhD in computer science without knowing math. I will tell you that right now. So you can scale out your cluster adding memory and processors. I have a 4-node Raspberry Pi cluster that's runs Spark that I built a few weeks ago. And it's really crappy compared to the one at ORNL, but it's still pretty cool. It's kind of sad that we now have $35 computers that can run faster than what we had 10 years ago even. I mean, it's not sad, it's great, but like they must have had a terrible job. So here's some good stats. At Spark Summit 2015, this was, 2015 in San Francisco, the largest node cluster someone had was 8,000 nodes. So that's 8,000 machines at however many gigs of RAM. And that was at Tencent. They're a Chinese tech company, very large, hundreds of billions of dollars in value. And there was a 1 petabyte single job at Alibaba, which is an Amazon competitor based in the East. And so they literally put a petabyte of data through Spark. And I don't know how much time it was, but the creator of Spark, Matteo Zari, I can't pronounce his name, he gave this case in the initial keynote. So that is actually that many bytes. That is 1,000 terabytes. So if you have 1,000 terabyte drives, they shove that much data through one job. That's actually 100 times the contents of the entire U.S. Library of Congress, which they basically have every book in existence. I think it's the Library of Congress. Would they not? I don't know. That's a lot of books. So why do we use Spark? I mean, why shouldn't we use something else? So I'm going to tell you a little about the benefits and drawbacks of using Spark versus something else. So one, it's very fast. Again, this is qualified by the amount of data you're trying to shove through it. Like I said, if you have a list of size 10 and you try and shove it across an 8,000 node cluster, it is going to take so much longer. I don't want to say exponentially, but a lot longer than if you did it with pure Python. So don't go throwing at that data. You can do it for fun, but there's lots of fun toy data sets to play with. It's friendly. The Python API, I have to say, for the fact that the people that wrote Spark wrote it in Scala, the Python API is incredibly Pythonic. It's very, very clean, very straightforward. And if you're familiar with Python's map and reduce functions and those kind of things, it's even easier to use. And the community is really good too. They had at least 1,000 plus contributors at the end of 2016. It's an Apache project, so they make a lot of guarantees about the stability. And some of the users include Pinterest, which uses it for the recommendations pipeline, Uber, which analyzes event and log data from all vehicles and endpoints across their entire fleet, which is lots of vehicles. And Netflix uses it for all the movies and TV show recommendations you get every day when you go home after work and do nothing. So why would you not use Spark? Well, let me go back and one more thing. This kind of goes into here. Spark also has a few things I forgot to mention earlier. As an entire machine learning library where you can run things like convolutional neural networks, the stuff that every company will tell you they're doing and it's better than everyone else. You can do that with one line of Python code. Really easy. You can do things like graph libraries. There's a library called GraphX, which is kind of similar to Python's graphing library. You can take something like Facebook's social graph and collapse it all into one and discover all your friends' secrets. There's GraphX, there's MLlib. There's a really, really, really cool library for any of you SQL people where you can turn an RDD, that long data set, into a data frame, which is similar to Pandas, which I'll talk about. And on that data frame, you can run straightforward SQL on RDDs. And it will distribute the SQL across all your clusters, and you are just writing SQL. That's it. The thing about that is that your columns need to be labeled. But if you know that you've got a data set, about all the favorite, Python libraries you have, and you have rankings for each one, and the first column is the library name, the second is the ranking, you can just pass that in and say select from all my Python libraries where the ranking is highest in descending order. And you can do that in RDD. And imagine there's 96,000 libraries on PyPI, last I heard, which was yesterday in a podcast. So if you have a favorite of all of those, then you can just write SQL across all that. It's great. And there's some other Spark stuff that we can throw. And the last one is Spark streaming. So again, we talked about Netflix has that pipeline. That's their streaming pipeline. So as you are browsing through movies and watching the newest episode of whatever is on, I was about to say Game of Thrones, but it's not on Netflix. That would have been a bad move. If you do that, it will be sending data across the wire, and Spark will be running actively, pulling that in and making recommendations. So that's the other component. So we have networking, or graphing, machine learning, the structured data query language, which is basically SQL, and then we have Spark streaming. So all these great things, why would you not use it? Again, I mentioned if you don't have much data, please don't use it. Spare your engineering managers the pain of you telling them your job took like 3 years to run. It won't take 3 years. If you can't use Java or run the JVM because you have a grudge out for it, then you can't use this as well. If you want to rewrite Spark's core in Python, please try. It will be terrible. It will not work. Just try and do that. I would love to see that. You don't have the sufficient resources. This is kind of crap, even though a lot of people give that a bad rep for that. If you have $5, you can spin up 100 nodes in Amazon for an hour and run Spark jobs on it on your own. I mean, it's super cheap. If you're at your company and if you're Uber, then you probably have the money to do it. If you're just wanting to demonstrate to your managers or your CEO or CTO that Spark is great, run it on just your machine and show them performance speedups like I showed you, and then they might invest in doing it. Or at home, just do it on your computer. I mean, you definitely have resources to run it. This isn't like a Cray supercomputer running at the lab or something. Still got time. So what if you want to use something else? There's plenty of other options. There's a lot of really cool libraries out there. Right now we have Python Dask, which is actually a really cool library. I haven't really messed with it much, but I'm hearing a lot of people talking about it. Which basically, at the end of the day, it kind of just reproduces Spark, but it's all in pure Python. And I can't remember if they use Python or not. I would hope they would do some kind of optimization there. Actually, I think it uses NumPy for the backend, so it is running all of the computation in C because NumPy is just C extensions. And NumPy, if you're not familiar, is an array library, basically a number crunching library in Python for all intents and purposes. We have Apache Storm, which is a project that Twitter has been a big fan of, and they, at least at one time, probably still now, using it to process their tweets. It's a streaming engine. We have Flink, which is relatively new, that kind of combines Storm and Spark and Hadoop into what they say is even better. You try at your own risk, but I've heard good things about it. And there's more growing by the day. If you want to write your own framework, that's why we're here. I mean, talk to each other, come up with something cool you want to do. Don't talk to me. I'm not that good. Probably can't do it. I don't have time either. But what if I don't have a lot of data? What if I just want to know about my data and explore my data and see that, hey, we have a data set of customers in our store, and we want to know why they come in at certain times. And we don't have a lot of processing to run. We just want to visualize some graphs and stuff like that. So I'll get into that. So Python can help a lot there too. But before we get to that, there's something you should know about if you're not familiar with it already. There's something called Anaconda. How many of you know what Anaconda is? Raise your hand. That's awesome. Just at least knowing about it is great. I'm glad you guys are here. Anaconda is cool. It's basically a distribution for data science. It's still Python. They didn't do any magic to it or anything. It's still straight up Python. But it contains a lot of the Python's most popular data science packages, as well as some Spark, as well as some Scala and R. And I don't know if they have Julia yet, but I know Project Jupyter, which is the notebook viewer, has Julia, which is a great new language for scientific computing, which I don't really know a lot about. And you can install over 720 more package libraries. So basically, Anaconda wraps up a lot of these really hard to install extensions. Like NumPy is already in C, so if you try and go install that in Windows, you will probably have an error if you don't have Visual Studio 2030 on your computer already. You can program Python 2 or 3, R, Julia in the browser with Jupyter, which is, if you ever see on GitHub or other websites someone doing interactive data science work where they have Markdown, and, nice text and then a graph and then some code, that's probably Jupyter. So if we do just want to explore this data and we don't really have a lot, or we have a good amount, we just want to look through it, you can use something called pandas. And I don't know if it's pandas or pandas, I just call it pandas. It's a Python data analysis toolkit. It's a fancy way of saying they provide two very key data structures that make life a lot easier. One of them is a series, which is a one-dimensional kind of list, and the other is a data frame, which is what you'll almost always be using. And the data frame can model a ton of relationships. Basically, anytime you have some variable that's related to another variable in some way, or maybe they're not related, and the graph will show you. And we provide operations for merging, reshaping, grouping, aligning, slicing. A lot of the stuff that Spark provides you with, Pandas will do as well. And when we talked about that Dask framework, Dask actually uses, I think it might actually use Pandas to do a lot of that stuff, or it uses NumPy, but it's similar to Spark in a lot of ways. And if you want to go at either one, they're both pretty straightforward to get into. Spark and Pandas. And it makes graphing as easy as just taking a data frame. If your data frame is named df, you just do df.plot, and it'll generate a graph with labels already there based on the data you gave it. We're not going to go too deep into pandas because I don't want to keep you too long. Maybe next year I'll come back and give a talk on that. Or go to any other Python talk, conference. They'll speak about it all the time. Matplotlib is literally from hell. It's really, it is very good. But if you want to like get data stuff, if you want to get graphing done quickly, I'll show you a few others. But that being said, if you publish papers or make articles or do anything where you need fine-grained control over Python visual analysis tools, Matplotlib is the thing you need to use. So it's a popular data viz library made by a guy that I think was very frustrated with MATLAB and how bad it is. Don't write MATLAB, please. It's again inspired by MATLAB's interface to graphing. A lot of people moved from scientific computing and MATLAB to Python because Python came about and had a lot of these libraries. I still think Python is the go-to library for data science. And anyone that tells you something like Ruby or Java is better, just please email me and I'll give you like 30 reasons to tell them why it's not. Because it's not. It's terrible. Really opinionated. We're here to Python comments. I can say these things. I feel like I can. Is anyone mad at that? A little bit, yeah. Well, I used to write a lot of C. I still write C, and I feel proud that I can say I wrote C and I understand it. But if I had to choose C over Python, I am choosing Python every day, unless I need speed. And if I need speed, I'll do it in Rust because Rust is awesome. So you should check out Rust. It can be rough around the edges, but it's very robust. And it's publication ready. In fact, the paper we just published at a security conference just got accepted 3 days ago. We used Matplotlib for everything. So other libraries, Seaborn is a very thin wrapper on Matplotlib. It makes things a lot prettier just by calling the same functions. Altair is something based on Vega or Vega Lite, which is a library, another visualization library that's part of Bash. Does anyone know what Vega is written in? Anybody? I think it might be JavaScript. I don't know, but it's another one. It's the new hipster framework, so check that out. ggplot is a Python library that's by Yhat that's based on ggplot2. Super confusing. I think Yhat skipped ahead of ggplot2, which is for R. So that's another good one. And Bokeh, that basically, instead of writing JavaScript, because we all hate JavaScript, you can take Python code and generate interactive graphs. I just spoke in November on JavaScript security because JavaScript has so many security flaws with it. So I think I can say that JavaScript is terrible. But if you see me there, don't tell them I said that. It's okay. It's a cool language. I like doing a lot of languages. So I think Python is cool, but it has its problems as well. Plotly is cool, but the problem with Plotly is it puts like a Plotly logo in the bottom right. But it is really cool in the sense that they provide a lot of wrappers and things to make your Python code turn into interactive visualizations in the web. And I'm going to put, these slides are already up in the link I'm about to show you, and I'll put them on my site too so you can get them. And I am recording it, so if you want to see it again later, I at least have the slides recorded and me talking. So pandas plus visualization tools is, again, very happy. So that's good. And I was going to do a demo, but I don't want to keep you guys here too long. But if you go to that link, I'll write it down really quick just so if you leave. I just want to go through this. But I put a Jupyter notebook there that shows some of those visualization tools and pandas. So that's HTTP. I feel like a professor. I have like 6 more years until I have my beat sheet up, so it's a lot. Let's see. Sorry, I should have thought of this beforehand. Okay, cool. That's that. And it's again on GitHub there too. So takeaways: big data processing can always be done in Python or with only Python. We can use things like Spark and do really cool large distributed tasks in Python. And again, Dask is another one, or Thrift, or Storm. A lot of those have libraries for doing stuff. You should consider frameworks like Spark or Dask to do this large-scale processing, and at least just try it out, even if you don't have a big data set. You can download tons of data sets online if you just Google open source data set. And I think there's even a GitHub repo for it. It's called awesome-datasets. Should be a lot there. And to manipulate and explore data on a small scale, you can use libraries like pandas and matplotlib or Seaborn or all those others. So that leaves us with questions and all the places you can find me online. So anybody have any questions? Yes?
So these RDD files and everything, those wind up on HDFS, or where do they go?
Yeah, so I mentioned RDDs, and Spark uses HDFS, which is Hadoop Distributed File System, and it is based in Google's Bigtable. I think it's Bigtable, which was what Hadoop used. And HDFS is what stores the data across all of your nodes. And we talked about those partitions or those tasks. They pull data out of HDFS. So you don't really have to even know that that's a thing. It's just underneath there. And it has things where you can connect to PostgreSQL and Mongo and text files and CSV and all that stuff too.
So you don't have to feed everything through memory first.
No, you can write. So basically, how we did in the lab when we had a large data set, we would just take. We had a directory of all these files, and I would just do like HDFS write or whatever the command line command is, and just point at the HDFS file directory, and it just throws it there. And it's actually kind of like a network file share. It just distributes that data across all your machines. Because the why this is so fast is because Spark will pull data only off the nodes that has an executor on that node for where that executor needs that specific data. So it doesn't have to reach back to a database. It's already on every single node. That's why when you get away from a standalone scheduler and just your machine, there's a little bit of complicated setup for this whole thing. I mean, it'll take you like 30 minutes to an hour, but you do it once and you can do it way quicker every other time. Yes?
So if you're using a cloud service for doing the processing, say a 2 petabyte file, do you have that network transfer time?
Yeah, so the cool thing about doing it like that, so I'll use Amazon as an example. Amazon has basically zero, if a very small amount, fees for transferring data within their cloud. If you try to upload the 2 petabyte data from your machine, as if you have that hard drive, to Amazon, you'll probably be in debt more than Bill Gates has money. So don't do that. But yes, Amazon has an API for pulling from those things and getting it in. They also have a bunch of data sets already in AWS. And I don't know much about Google Cloud or Azure, but I'm sure they're probably similar. Because they realize that people are going to do that. And they're not going to try and block people out of, charging. Does that answer your question? Okay. So yeah, he asked whether the cloud services have ways to get data in and out, or how do you get them out, that kind of stuff. Any other questions? Is that it? Okay, thank you guys for having me.